today. A theoretical physicist says the answer is maybe. He suggests a Manhattan-sized object known as 3I Atlas could actually be a mysterious alien.
Consider a black swan event, an event that you put a small probability for it happening, but you look at anomalies in the data and say, look, the implications are so huge, we have to consider it. And therefore, we should consider the possibility that things like us existed long before us.
In October 2025, astronomers around the world watched in astonishment as a familiar interstellar visitor, 3I Atlas, reached Perihelion, its closest approach to the Sun, during its outbound journey from deep space.
The news yesterday was that this object came closest to the Sun, and it received a huge amount of heat from the Sun. And the latest report indicates that it became extremely bright, much more than expected.
But what was expected to be a routine observation quickly turned into a cosmic mystery. 3I Atlas began exhibiting behaviors no comet, asteroid, or known interstellar object should display. Unusual brightness fluctuations, unexpected jet activity, and a tail that appeared to defy solar winds left experts scrambling for explanations. Was this simply an extreme natural anomaly, or were we witnessing the first signs of something far stranger, perhaps even artificial? Tonight, we'll explore everything you need to know about this anomaly, its implications for astronomy, and what it could mean for our understanding of interstellar objects. The anomaly at Perihelion. Perihelion has always been a critical event for the observation of comets, asteroids, and especially interstellar objects like 3I Atlas. It is the point in an object's orbit when it comes closest to the Sun, receiving the maximum solar radiation and heating. For ordinary comets, perihelion is a predictable phase. Ice sublimates, dust, and gas are released, and the comet brightens gradually. Its tail forms under the influence of solar wind and radiation pressure, always pointing away from the Sun. But 3I Atlas, during its perihelion in October 2025, defied every expectation, displaying a series of behaviors that left astronomers both baffled and exhilarated. The observations made during this period marked a turning point in the study of interstellar objects, highlighting the need to reconsider fundamental assumptions about their nature and potential complexity. Ground-based observatories and space telescopes around the world quickly began monitoring 3I Atlas as it approached perihelion. Early data showed the object brightening in patterns unlike any comet previously recorded. Instead of a smooth, gradual increase in luminosity as sublimation accelerated, 3I Atlas exhibited sharp spikes of brightness at irregular intervals. These fluctuations were non-random and highly structured, suggesting a mechanism beyond simple physical outgassing. Researchers noted that the light curve, the graph of brightness over time, was punctuated by sudden surges that recurred inconsistently. This anomaly immediately raised questions. Was the object spinning in a way that exposed reflective patches intermittently? Or was there a more exotic explanation at play, perhaps something engineered or artificially influenced? The idea of rotational influence gained traction when astrophysicists analyzed the photometric data in detail. Spin phase modulation, a term used to describe subtle, systematic changes in rotation rate, was clearly detectable. This jitter, correlated with the brightness spikes, suggested that the object's rotation was not random or passively influenced by solar torque alone. Ordinary comets, irregular shapes, and outgassing can cause rotational changes, but the degree and timing observed in 3I Atlas were unlike anything previously documented. It was as if the object had an internal system capable of controlling or adjusting its rotation to produce specific observational effects. Such a capability is unheard of in natural interstellar comets, and it immediately drew the attention of scientists across multiple disciplines, from astrophysics to planetary science. Perhaps the most visually striking anomaly during perihelion was the behavior of 3I Atlas's tail. Comet tails, under normal circumstances, are sculpted by the solar wind and radiation pressure. They point away from the Sun, and their curvature and brightness follow predictable physical laws. Yet, observers reported the phenomenon of a tail reversal, where parts of the luminous tail appeared to point toward the sun instead, known as an anti-tail. This effect is exceedingly rare and usually explained by specific geometric or perspective alignments from Earth, combined with the distribution of dust particles. However, for 3I Atlas, the anti-tail was consistent, pronounced, and not dependent on observational angle alone. Its persistence suggested that the object was actively emitting material in a way that countered solar pressure, as if it could generate thrust or manipulate its immediate environment. This behavior added another layer of intrigue, raising possibilities that challenged conventional astrophysics. Adding further complexity, amateur astronomers contributed crucial observations. Enthusiasts from Thailand, Europe, and other parts of the globe reported transient flashes and unusual luminous patterns along the surface of 3I Atlas. These were fleeting, often lasting only a few seconds, yet they were recorded independently by multiple observers, making it clear that they were not artifacts of equipment or atmospheric distortion. The flashes hinted at reflective or metallic surfaces, suggesting that parts of the object were composed of materials denser and more cohesive than the porous ice and dust typical of comets. These observations also implied heterogeneity in surface composition, with reflective patches appearing in certain areas and behaving differently under solar illumination. In short, the object was not behaving like a uniform mass of ice and dust. It was complex, structured, and dynamically active. The perihelion behavior of 3I Atlas has also prompted serious debate about the possible origin of such an object. Traditional models of interstellar comets envision small, icy bodies ejected from distant stellar systems, wandering through interstellar space in irregular orbits. They are expected to be relatively simple, passive objects, shaped primarily by gravitational forces and solar radiation when entering a new system. 3I Atlas, however, exhibited dynamics that exceeded these expectations. Its rotation, brightness fluctuations, anti-tail, and possible reflective surfaces all hinted at a level of sophistication that is extremely difficult to reconcile with standard formation theories. Some scientists have speculated that we may be observing an object that is either unusually evolved or engineered, a prospect that, while speculative, cannot be dismissed given the anomalous data. Another aspect of perihelion that captured attention was the correlation between observed behaviors and solar activity. During the October 2025 perihelion, 3I Atlas coincided with a period of moderate solar activity, including small coronal mass ejections, CMEs, and solar flares. While these events were not extraordinary on their own, researchers noticed subtle correlations between bursts of solar energy and increases in the object's brightness or activity. This raised the question of whether 3I Atlas was merely responsive to solar stimuli in a natural, reactive way, or whether it possessed internal mechanisms that allowed it to harness or counteract solar influence. The interplay between an interstellar object and the Sun added another layer of complexity to an already puzzling set of observations. Advanced simulations have been employed to model 3I Atlas's behavior. By inputting rotational data, brightness fluctuations, and tail dynamics, researchers have attempted to reconstruct the object's internal structure and energy distribution. Some models suggest that internal chambers, vents, or reflective surfaces could explain observed phenomena. Others propose that the object might have irregular density distributions with heavier, reflective patches embedded within lighter icy matrices. While none of these models can definitively account for all observations, they underscore the need to expand our theoretical frameworks. 3I Atlas challenges our assumptions about what interstellar objects can be and how they behave under extreme solar conditions. The global nature of the observational campaign has also been unprecedented. Data sharing between professional observatories, space-based instruments, and amateur astronomers allowed for continuous monitoring across multiple time zones. This collective effort provided a near real-time understanding of the object's dynamic behavior. capturing fleeting events that might otherwise have gone unnoticed. It is a testament to modern astronomy that such a small, distant object can be tracked with precision, revealing complex behaviors in unprecedented detail. Importantly, the anomalies observed at Perihelion have implications beyond 3I Atlas itself. They raise questions about the population of interstellar objects in general. If 3I Atlas is representative, even partially, it suggests that interstellar space may contain objects with more varied and complex structures than previously imagined. The standard picture of rogue comets and asteroids drifting silently through the galaxy may need to be revised to include bodies capable of dynamic behavior, internal heterogeneity, and even active environmental manipulation. Each new observation reshapes our understanding of the cosmic neighborhood and the diversity of material drifting through it. The October 2025 perihelion of 3I Atlas represents one of the most compelling astronomical events of recent years. From rapid structured brightness fluctuations to anti-tail phenomena and rotational modulation, the object defied expectations at every turn. Amateur and professional astronomers alike contributed to an unprecedented observational campaign, capturing subtle but significant features that challenge existing models of interstellar objects. The implications are vast. Whether 3I Atlas is a naturally complex body, a highly unusual interstellar comet, or something engineered, it forces scientists to rethink assumptions about the diversity and capabilities of objects traveling between stars. The perihelion anomaly of 3I Atlas stands as a reminder that the universe still holds countless mysteries, many of which are closer and more observable than we might expect. With each observation, new questions emerge. What caused the anti-tail? How are the brightness spikes coordinated with rotation? What does the internal structure of the object look like? These mysteries ensure that 3I Atlas will be studied for years to come, inspiring curiosity, debate, and possibly new scientific paradigms. It is a rare event that combines wonder, challenge, and discovery, illustrating the vast complexity of the cosmos and our growing ability to witness it in real time. Observational challenges and agency silence. One of the most perplexing and fascinating aspects of the 3I Atlas perihelion anomaly was not merely the behavior of the object itself, but how the very act of observing it became fraught with disruptions at the exact critical moment. For astronomers and space enthusiasts around the globe, this coincidence was extraordinary, prompting questions that extended beyond conventional astrophysics. As the object approached its closest point to the Sun in October 2025, the usual flow of observational data, streams of measurements from both space-based and ground-based observatories, seemed to falter in unusual and inexplicable ways. Key solar observatories that had long provided uninterrupted monitoring suddenly reported temporary outages, while some of the world's most advanced telescopes experienced telemetry gaps that could not be immediately explained. Space-based instruments such as the Solar and Heliospheric Observatory, SOHO, and NASA's GOES-19, which continuously monitor solar activity, recorded these unexpected lapses during a period when continuous data was most critical. Normally, any minor disruption in data flow might be attributed to technical issues or routine maintenance. However, the timing here was extraordinarily precise. The outages coincided exactly with 3I Atlas's perihelion, a phase of its trajectory that astronomers were monitoring intensely. This alignment between the object's position and the observational anomalies raised eyebrows across the scientific community. Was this an improbable coincidence, or was there something more profound occurring, something that challenged both the predictability of space weather and the reliability of our observational networks? Adding to the intrigue, NASA's Deep Space Network, DSN, responsible for communication with spacecraft across the solar system, temporarily redirected several of its major antennas during the perihelion window. The agency did not provide public explanations at the time, creating a vacuum of information that only fueled speculation. Similarly, the European Space Agency, ESA, postponed routine updates related to deep space tracking, including details on distant comet monitoring and planetary missions. While such operational adjustments might be standard in some contexts, their exact synchronization with 3I Atlas's perihelion raised the possibility that these institutions were aware of, or at least preparing for, anomalous activity that was not meant to be publicly disclosed. Amateur astronomers and radio hobbyists were quick to note additional peculiarities. Starlink satellites, along with other low Earth orbit communication constellations, were observed entering protective modes or altering their operational behavior. These maneuvers are generally triggered to protect satellites from increased radiation, particularly during solar flares or coronal mass ejections. However, during this perihelion event, there were no major solar flares reported that would explain such widespread precautionary measures. Observers speculated, was the object itself interacting with the local electromagnetic environment, creating conditions that prompted satellites to respond automatically? Or was there a preemptive measure taken by agencies that overlapped with natural precautions, producing a layered effect of anomalous activity and secrecy? Behind the scenes, a network of private astrophysics forums, independent observatories, and research groups began piecing together patterns that were subtle but persistent. Electromagnetic readings, particle flux data, and light curves from different observatories started revealing correlations that could not be dismissed as random noise. For instance, the object's brightness variations, already highly unusual compared to typical cometary or asteroid behavior, showed a temporal alignment with small spikes in local particle detection. Light curve analyses revealed fluctuations that were non-random and complex, suggesting that the object was exhibiting internal dynamics or structural features influencing the way it interacted with sunlight and solar wind. What made these observations particularly compelling was the duration of the anomalies. Random disruptions or transient solar activity usually resolve quickly and unpredictably, but the data irregularities surrounding 3I Atlas persisted long, enough to warrant serious scientific scrutiny. The sustained nature of these anomalies implied a repeatable or at least extended mechanism at work. Researchers began speculating whether the object's trajectory or physical characteristics were influencing the solar environment in measurable ways. Could 3I Atlas, for instance, be altering the flow of charged particles near it, or even affecting electromagnetic readings from satellites in its vicinity? If so, such behavior would be unprecedented, potentially reshaping our understanding of how interstellar objects interact with the Sun's magnetosphere and the inner solar system environment. The convergence of multiple unusual events, a bright interstellar object, sudden satellite protective modes, telemetry gaps, and light curve anomalies created a fertile ground for intense scientific and public speculation. Discussions erupted across professional and amateur channels alike. Astrophysicists debated whether these phenomena could all be explained naturally. Could an unusually dense or metallic composition cause 3I Atlas to reflect sunlight in a manner that influenced nearby sensors? Could it carry volatile compounds that reacted unpredictably when heated during perihelion? Some suggested the object's rotation and reflective surface features might generate minor electromagnetic effects, detectable only by sensitive instruments. While plausible in theory, none of these explanations fully accounted for the coordinated nature of the observations and the precise timing of the anomalies. Some in the community quietly considered the possibility of artificial influence, not necessarily intelligent intervention, but perhaps an unknown structural property that enabled the object to survive the intense radiation near the Sun in ways natural models could not predict. Could 3I Atlas possess internal cavities or chambers, akin to vents in a spacecraft, that allowed it to stabilize rotation or control outgassing patterns under extreme solar heat? Could these features inadvertently interact with sensors or create localized electromagnetic perturbations? While such hypotheses remain speculative, they illustrate just how disruptive the perihelion anomaly has been to conventional scientific thinking. Meanwhile, independent observatories around the world began cross-verifying observations. Telescopes in Europe, Asia, and the Americas contributed additional photometric data, revealing that the light curve anomalies were consistent across multiple instruments and geographic locations. This global confirmation suggested that the phenomena were not due to local instrumental error, atmospheric distortion, or data processing glitches. Each new data set added nuance to the emerging picture. 3I Atlas was not behaving like any comet or asteroid previously observed, and its interaction with its environment, both solar and observational, was far more complex than anyone had anticipated. Furthermore, particle detectors, onboard satellites, and ground-based magnetometers detected small but measurable deviations coinciding with the object's passage through perihelion. These variations were subtle, yet distinct enough to rule out random solar fluctuations or instrument noise. Scientists began analyzing whether charged dust or outgassing from the object could create such effects, but the consistency of the readings suggested a more structured phenomenon. The interplay of brightness spikes, anti-tail phenomena, rotational jitters, and now observational anomalies painted a picture of an object that might be uniquely capable of interacting with its surroundings in ways that transcend known physics for natural celestial bodies. The perihelion anomaly has implications that extend beyond mere curiosity. If these behaviors are natural, they indicate that interstellar objects can carry physical complexities previously unimagined: self-modulating rotation, unusual reflective properties, and subtle environmental interactions. Such findings would demand a re-evaluation of models for comet formation, interstellar material survival, and orbital dynamics for objects traveling across light years. On the other hand, if any level of artificiality or engineered design is at play, even in part, humanity may be witnessing the first tangible evidence of an interstellar probe passing through our solar system, a discovery with implications for SETI, search for extraterrestrial intelligence, planetary defense, and our understanding of what is physically possible in object construction beyond the solar system. Regardless of the interpretation, the perihelion anomaly underscores a profound truth. The universe still holds surprises that defy expectation and challenge established models. Observatories, both professional and amateur, are now coordinating to maintain long-term monitoring of 3I Atlas as it recedes from perihelion. These efforts aim to capture continued brightness fluctuations, rotational dynamics, tail behavior, and any further interactions with the solar environment. Each new observation provides the potential to unravel some part of the mystery, offering insights into interstellar physics, object composition, and possibly the limits of natural celestial mechanics. The broader impact of the anomaly is also cultural and philosophical. Events like the perihelion of 3I Atlas remind humanity that even in an era of unprecedented technological capability, the cosmos retains the power to surprise, to confound, and to inspire. The precise timing of observational disruptions, the potential coordination of protective measures by satellites, and the independent verification of anomalies by global observatories all contribute to a sense of mystery and excitement. For professional astronomers, it is a call to revisit assumptions about interstellar objects. For enthusiasts, it is a narrative that blends wonder, science, and the tantalizing possibility of the unknown. In practical terms, the perihelion anomaly has also served as a testbed for observational techniques. Instruments and software designed to track solar and interstellar phenomena are being pushed to their limits, revealing both strengths and vulnerabilities in global monitoring networks. The ability of the international scientific community to coordinate observations across continents, integrate satellite and ground-based data, and cross-check results in real time demonstrates the sophistication of modern astronomy while highlighting the persistent gaps in our understanding of complex, fast-moving objects. The perihelion anomaly of 3I Atlas is not merely a curiosity. It is a landmark event in modern astronomy. The combination of temporary observational disruptions, Non-random brightness fluctuations, rotational anomalies, anti-tail behavior, and correlated particle readings creates a scenario unlike any previously recorded. Whether natural or artificial, 3I Atlas challenges established paradigms, tests the limits of observational technology, and invites the global community to rethink the nature of interstellar objects. As it continues its journey beyond the Sun, astronomers will remain vigilant, seeking answers to questions that touch on the very fundamentals of physics, celestial mechanics, and our place in the cosmos. One thing is certain: 3I Atlas's Perihelion anomaly has already rewritten the rules of what we thought we knew about interstellar travelers, turning a simple observation into a profound and ongoing cosmic mystery. Implications for interstellar science. 3I Atlas's Perihelion anomaly may represent one of the most profound challenges to modern astronomy in decades, potentially rewriting our understanding of what interstellar objects are truly capable of. When this object first entered the solar system, astronomers immediately recognized it as extraordinary. Its hyperbolic trajectory confirmed its interstellar origin, meaning it had traveled across light years of space before encountering our Sun. Yet, as remarkable as that alone was, the behavior it exhibited during perihelion, a point in its orbit closest to the Sun, was unprecedented. The anomalies observed during this period suggest that interstellar objects may be far more complex than previously assumed, exhibiting behaviors that force scientists to question not only their physical nature, but also the limits of known cosmic physics. If we consider 3I Atlas as a natural object, the implications are staggering. Its perihelion anomaly has already altered the landscape of astronomical research. The object challenges assumptions, inspires global collaboration, and forces a re-examination of both cosmic physics and the potential for intelligent life beyond Earth. As we continue to observe its journey outward from the Sun, one truth is undeniable. 3I Atlas has transformed a routine study of interstellar debris into a profound exploration of the unknown, where every observation may bring humanity closer to understanding the complexity, diversity, and mystery of the universe itself.